Welcome to my class 12 physics. Today we will discuss about electric potential at any point due to a point charge. And before discussing this topic, let us recall the point electric potential, the meaning of the electric potential. Look at the figure. Here two charges are there. One is your plus Q, capital Q, that is the source charge, situated at the origin. We write that is point O. Another charge is there, second charge, that is the plus Q0. This is known as the unit positive test charge. Unit positive test charge. And magnitude of this charge we take, that is 1 coulomb. Then two charges are there. One is a source charge, another is a test charge. Both are positive. So that the source charge repel the test charge along this direction. That means a force is applied on this unit positive test charge along this direction. That force is known as the electrostatic force. And initially the unit positive test charge situated at infinite. This is the initial position. Now we applied a external force on this unit positive test charge, and magnitude of this external force may be equal to or slightly greater than the electrostatic force, and its direction is just opposite to the electrostatic force. Then what happens? Suppose one force is positive, another force is negative, then a net force applied on this charge, that is Fe plus F external, that is equal to 0. If a force is equal to 0, acceleration is 0. If acceleration is equal to 0, then the unit positive test charge moves now towards the point P by this force with a constant speed, because acceleration is 0. That means finally we get, by the help of this external force, now the unit positive test charge starts to move from infinite up to point P. So that work is done by this external force, and you know that work done is known as the electric potential. Clear? And we have studied this. And this is the mathematical expression of the electric potential. That means for potential we write the symbol V. We write here Vp. Vp means potential at point P due to the source charge. Potential at point P due to source charge, we write that is Vp is equal to work done divided by unit positive test charge. That means simply we write potential is equal to work divided by charge. Charge means that is unit positive test charge. And this is all about your electric potential. But today we will discuss about this point, that is potential at any point. Potential at any point due to a point charge. This one is the figure. Here this is the source charge, that is plus Q, situated at the origin initially, and we take a unit positive test charge plus Q0 initially present at infinite. You know both are positive, so that a repulsive force is applied. Suppose this is the positive x-axis, suppose, that means direction of the repulsive force, electrostatic repulsive force is along the positive x-axis. And we applied external force just opposite to the electrostatic force. Then what happened? The unit positive test charge now starts to move towards the point P without any acceleration, and after some time or at any instant of time, suppose this is the position of the source charge. Sorry, this is the position of the test charge. And you know magnitude of the test charge, that is 1 unit. So that in SI we write that is 1 coulomb. That means source charge is situated at point O. Now at any instant of time, the test charge is situated at point A. Then distance between O to A we write that is x. Then force between these two charges. These two charges means one is your plus q0, another is plus q. If distance between the two charges is x, you know from the Coulomb's law, force F is equal to 1 divided by 4 pi epsilon 0. Magnitude of the first charge we write q1, magnitude of the second charge we write q2 divided by square of the distance between the two charges. Here we applied the same formula. We write 1 by 4 pi epsilon 0, magnitude of the first charge, that is capital Q, magnitude of the second charge, that is 1, so that in place of q2 we write 1, divided by square of the distance, a distance between the two charge, that is x, so that in place of r square we write x square. This is the force applied between the source charge and the unit positive test charge when the unit positive test charge is situated at point A. Clear? Now, we give some time to this unit positive test charge, very small time. Very small time means suppose that is del t. In del t time, now the unit positive test charge starts to move from point A to B. Very small distance, small time, small distance. So that distance between A to B, that is also small, that is del x. And this is the direction of the displacement. This is also direction of the electrostatic force. This is the direction of the external force. And this is the direction of the electrostatic force. Now, we calculate work done due to this displacement. That means due to displacement del x, work done is equal to small, we write that is del W. Now we write del W is equal to force multiplied by displacement. Here two forces are there, one is electrostatic force, another is external force. If we take the external force, angle is 0 degree because this is the direction of the external force. This is also direction of the displacement. Both are in the same direction, so that theta is 0 degree. Clear? If we take the electrostatic force, this is the direction of the electrostatic force, but the unit positive test charge moves along this direction. Both are in opposite direction, so that we take theta is equal to 180 degree. Here we take the electrostatic force Fe, and you know work done W is equal to F dot S. You know this formula. Work done W is equal to force F dot displacement vector. That maybe you write S or you may also write R. Here we take in place of F we write electrostatic force, dot product is there multiplied by displacement. This is small displacement. An angle between the electrostatic force and displacement is 180, so that we write cos 180 because dot product means you know vector A dot vector B is equal to AB cos theta. This is the dot product between the two vector. Another is cross product between the two vector. You also know that. That is A vector cross B vector is equal to AB sin theta. For direction we write that is n cap. You know this product, dot product and cross product. And in place of cos 180 we put minus 1, so that the expression is minus of force multiplied by displacement. What is force? This is the expression of the force, so that in place of Fe we put equation 1. So that we write minus of 1 by 4 pi epsilon 0 q divided by x square multiplied by del x. This is the work done. This is the work done when the unit positive test charge moves from point A to B. That means if a displacement is del x, this is the expression of the work done. Very simple. But here the unit positive test charge moves from point infinite up to point P. Up to point P means at a distance r from the source charge. So that here we will calculate the total work done. Here we will calculate the total work done when the unit positive test charge moves from infinite to point P. From infinite means this is the initial position. This is the initial position. That means this is the lower limit. P point is the final position. So that is known as the upper limit. That means we write total work done is equal to same expression minus of 1 by 4 pi epsilon 0 q by x square into dx, and the charge particle moves from infinite up to point r. And here q divided by 4 pi epsilon 0 we take outside of the integration, only remaining is equal to this one. If we solve this integration, here we use the formula of the integration, that is integration of x to the power n dx is equal to x to the power n plus 1 divided by n plus 1, you know this one. And here in place of n, minus 2 is there, so that we write integration of x to the power minus 2 dx is equal to x to the power minus 2 plus 1 divided by minus 2 plus 1 is equal to x to the power, this is minus 1 divided by minus 1 is equal to minus of 1 by x. This is the answer. So that in place of integration of x to the power minus 2 dx, we write that is 1 by x, and the lower limit is infinite, upper limit is equal to r. If we solve this one, then we write this is equal to q divided by 4 pi epsilon 0. First, in place of x we put the upper limit, that is r, so that we write 1 by r. Then minus sign is there. Next, in place of x we put the lower limit, that is infinite, so that we write 1 by infinite. And you know 1 by infinite is approximately 0 or tends to 0. Remaining is equal to work done W, and that work done is the electric potential. So that we write work done W is equal to potential V at a distance r from the source charge is equal to 1 divided by 4 pi epsilon 0 q divided by r, and this is the final expression of the electric potential at any point. At any point means in this case that is at point P, and next point, that is suppose source charge is negative. If source charge is negative, then what is the expression of the electric potential? Simply, if source charge is negative, that means source charge is q is less than 0, then work done by the external force per unit positive test charge in bringing it from infinite to the point P is negative. That means very simple. If source charge is positive at a distance r, that means at point P, potential is positive. If source charge is positive at a distance r, potential is positive. If source charge is negative at a distance r, potential is negative. If distance is infinite, if at an infinite distance, then potential is 0. Clear? Now, we draw a graph, that is variation of electrostatic potential and field with distance. Variation of how electric potential and electric field vary with the distance. Clear? And you know, suppose a charge is there, that is plus q, and at a distance r from this charge, suppose this is the observation point, we write P. At point P, you know the value of the electric field, you have studied it in this in the first chapter, that is E is equal to 1 divided by 4 pi epsilon 0 q divided by r square, if this distance is equal to r. You know this formula. Similarly, you also know the expression of the potential V is equal to 1 divided by 4 pi epsilon 0 q divided by r. This is the expression of the electric field at point P. This is the expression of the electric potential at point P. Clear? Suppose this distance is equal to 1 unit. R is equal to 1. That may be 1 meter in SI. That means if in place of R, if we put 1, then this expression becomes E is equal to Q divided by 4 pi epsilon 0. Similarly, if in place of R we put 1, then this expression also becomes V is equal to Q divided by 4 pi epsilon 0. Look at these two expression. This is the expression of the electric field. This one is the expression of the electric potential. Both are same. Both are same. That means simply finally we write if R is equal to 1, then field is equal to potential. If R is equal to 1, then field is equal to potential. Now look at the graph. This is the point. This is the point. Here along the x-axis we take the distance, that is R. Along the y-axis we may take, that is the potential V or field E. And here distance R is equal to 1. If distance R is equal to 1, then at this point electric field is equal to electric potential. This red one, this red graph for the electric field, and this blue graph, that is for the potential. And from the equation here, from this equation we write electric field is inversely proportional to square of the distance. From this expression we write potential is inversely proportional to the distance. Here this is the square of the distance. Here only distance is there. Here electric field is inversely proportional to square of the distance, but here potential is inversely proportional to only distance. So that if we compare these two, electric field decreases more rapidly. Electric field decreases more rapidly as compared to the potential. Because E is inversely proportional to square of the distance only due to this. Clear? And this is the point of intersection. And we have discussed this. Point of intersection means R is equal to 1. That means if R is equal to 1, field is equal to potential. And another point is that before the point of intersection. Before the point of intersection means value of the R is less than 1. That means this is the situation, R is less than 1. If R is less than 1, then what happens? Suppose one example. So this is the distance. Means distance R is equal to 0.5. If R is equal to 0.5, what is the value of the potential? This is the value of the potential, that is 2. What is the value of the field? This is the value of the field, that is 4. That means if distance R is equal to 0.5, potential is equal to 2, field is equal to 4. That means magnitude of the electric field is greater. As compared to the magnitude of the electric potential. What is the condition? Condition is distance is less than 1. So that you write, if distance is less than 1, that means R is less than 1, that is known as the before intersection, then electric field curve stays above the potential curve. Electric field curve stays above the potential curve. Clear? Similarly, another point is there, that is after the intersection. Means R is greater than 1. If R is greater than 1, here we write electric field curves below the potential curve. This is the electric field curve, that is below the potential curve. Clear? And this is all about your electric potential at any point due to a point charge. And this is the graph, means variation of electric field and potential with distance. And in the next class we will discuss another new point, that is electric potential due to a dipole on axial line. Electric potential due to a dipole or electric dipole on the axial line. Clear? Thank you.